of nanoscience and nanotechnology. Is still part of Spain?
Well,
it will be about the 2D semiconductor nanostructures at the atomic scale. So Jordi was always working in Barcelona, where he's also vice president of the Spanish Microscopy Society, and is nowadays the leader of nanoscience and nanotechnology group in Barcelona. Okay? So yeah, please, you can start. Thank you.
So, first of all, thank you very much to the organizers. Something was wrong, now I'm the president of the Spanish Microscopy Society.
Congratulations.
As far as we are in Spain, so that is another thing. So, let me thank you very much to the organizers for letting me be here. It's my second year in ANNIC, so I will try to change the topic and do some more stuff not presented last year. So it's a pleasure to be in Rome, such a wonderful city. And, well, that doesn't work.
It's on? No. Your pointer is on?
Yeah, sure.
But let's start with this one. No.
It was working before. So sorry.
Okay, if it was working, please, this one.
Nice. Okay. Sorry about that, but it was working before. So, yeah. So we are in Spain or not, I don't know. So by now we are, and this is our situation here. You may know about the news that there is important mess there. So let's see what will happen in the next month or days. Maybe. So I'm coming from Barcelona. Here, the Mediterranean shores, just at the other side. I mean, it's close to Rome as a straight line. So at the other side of these really nice mountains, you have the pretty city of Barcelona. You have the ICN, the Catalan Institute of Nanoscience and Nanotechnology. So we are in the UAB campus, the University Autónoma of Barcelona, and just very close to the ALBA synchrotron. So we are belonging also to this amazing network of NFFA. So if you want to apply, we can also supply you some help through this European project. So we are a group of microscopists, so we work with many different materials from many different groups, and it's especially interesting to work with the groups that we are there in the University Autónoma of Barcelona and also in the surroundings of Barcelona. So we have 7 different universities around Barcelona, so the amount of materials is amazing. But we also collaborate with many groups from abroad. So our topics are several, from nanoparticles and plasmonics, oxides and ceramics, but mostly on freestanding nanostructures and nowadays nanostructures for energy. So these two topics are sometimes related because you can have these photonic properties, electronic properties, but also they can be applied for energy applications. So the thing is that what is a freestanding nanostructure? So it's everything that is growing up from a substrate, not a thin film, but it can be a nanowire, it can be a nanomembrane. So this is why today I will also talk about these 2D nanostructures, okay? A nanomembrane, for us, it can be a nanostructure. So for those that don't like to mention or don't like to say that this is a 2D nanostructure, I will also show you, for example, nanoflakes made of molybdenum sulfide. They are really 2D materials with one single monolayer. So let's start by this. These materials, which are freestanding, they can grow as a nanowire, like vertically like this type of nanomembrane, and they have really nice electronic properties, really nice photonic properties, and also important energy properties. The point here is that in order to understand all these properties, it will be very important to understand these materials from the atomic point of view. So at the tiny state of every atom, when we see them, we can understand and modelize how these materials are working. So why I'm showing it here, I was showing it also last year, but it's important first of all to understand why I'm talking about microscopy. So electron microscope was made many years ago, but in the last 20 years there has been a strong revolution here. And the strong revolution maybe Odile was explaining it also yesterday, but the good thing is that if we compare it to the telescope, Hubble, in the United States, that wanted to create a telescope that get rid of the aberrations that the atmosphere is giving. So the great idea was, let's take the telescope, put it in the outer space, and then the resolution will be amazing. So that was the first image they were obtaining. It's a disaster. You cannot see anything there. It's maybe a galaxy, it's a star, I don't know what is that. So the problem is that the telescope was perfect. In the Earth, it was working perfectly. But then due to the acceleration of the rocket, when it was going to the outer space, the mirrors here were deformed. Just a few millimeters, but it was enough in order to introduce to the lenses a huge spherical aberration. So with the microscopy, it's exactly the same. In that case, I mean, they sent these guys up there, they tried to polish a little bit the mirrors, they were also working with the software, and at the end, we could see that the images that we can get now from the Hubble telescope are amazing. So exactly the same. You can move this to the electron microscopy, and you can see that with the correctors, with the aberration correctors, what we can get are higher peak intensity, better contrast, and much, much higher resolution. So nowadays, we're able to say that we can see atoms individually, okay? So our aim is that this is a big, huge nanowire, okay? This is a quantum dot with barely 2,000 atoms, but we want to see this tiny atom that is there, only one of them. So what we are doing is trying to scan with an electron beam all our material, go right there where our single atom is, and try to detect it and extract the different properties that it may have. So this is the deal, and I will try you to show with examples what we are trying to do. So the first thing, this is a non-aberrated corrected image, so you cannot almost see anything. You apply the corrector, and you can see the atoms. So this is the thing here. So, in order to understand our materials and the first 2D structures that I will explain, it's important to speak first about polarity and which are the mechanisms that are producing these structures. So, from the atomic point of view, I will talk about two main structures that create most of these binary semiconductor materials, like gallium phosphide, gallium arsenide, silicon itself. You can have the ABC stacking of the typical cubic structure, or you can have the zigzag AB stacking of the bursite hexagonal structure. Both are more or less, let's say, the same when you are seeing along this 111 direction or this 0001 direction. So both are more or less equivalent, and you will see. So at the atomic scale, they look like this. So you can see perfectly the atoms here, how they are stacking. This is the ABC stacking of the atom, and this is the zigzag AB stacking here. So the minimum, let's say, reference of the atoms here is this binary system that is composed, we call it tangle. So you have here the anion and the cation of all the atoms. So these are facing to one direction, and you can see that in one direction, the cation is facing on top, but on the other direction of these 111 planes, the cation is facing on the other side. And here it's the same. The anion is on one side, and the cation is on the other side. So these materials are polar, because you have an electrical field that is produced inside this material. This is giving rise to many properties to these materials. For example, in gallium nitride, and for example, in zinc oxide, you have this piezoelectricity. You have many different defects at the quantum scale that can be applied here. But it's important to see how these materials are composed. So we've been analyzing many of these different materials, all the 3,5 composites in nanowires, for example, all of these 2,6 composites. And what we have seen is that in many of the growth conditions that these materials are growing, in most of the times these materials are growing in big polarity. So that means that the anion is always on the top. So nitrogen, phosphor, arsenic, or antimonium is always on top and is driving the force of the growth of these materials. If you try to change the polarity of these materials under the same growth conditions, these materials are not growing at all. You can tell me that I'm a liar. It's not exactly true, because if you change the growth conditions, then you change the growth rate, then the growth is not so fast as in this case, and you can grow in the reverse polarity. So in some applications, reversing the polarity is very interesting. And nowadays, many groups, and many of the groups with we are collaborating, we are trying to reverse polarities and play around with that, because you have a lot of quantum properties that can arise from this. But in the normal growth conditions, that in the last decade people were growing the nanowires, most of the materials were growing with this anion always on top. But there is one exception. In zinc oxide, it was always zinc which was on top. Okay? And this gives, I will not talk about this today, but this was giving several really nice properties when you were mixing materials of this side with zinc oxide, because there was a reversal of the polarity. So this is the typical 1-1-1 direction. I told you that it can be terminated in arsenic or either in gallium, and only the anionic polarity is the one that is giving rise to the growth of these materials. So you can understand that if this is a typical octahedra composed of 8 1-1-1 planes, only the ones terminated in yellow color, that is the arsenic, will allow the growth. So if you have this octahedra here, imagine that the first nucleation seat on top of your substrate is terminated in arsenic, then you will allow the growth of vertical, really nice nanowire. But what happens when this is inversed? If the top layer is terminated in gallium, we cannot grow vertically, but we are allowing 3 other facets at 19 degrees that are terminated in arsenic, and it will allow the growth not in the vertical direction, but in some other angle direction. Typical nanowire. This is gallium arsenide nanowire. This is the nucleation seat. It's not an octahedra. The octahedra was only used to illustrate which are the possible facets. But we can see that here, the top facet or the top termination in every one single 1-1-1 plane is the arsenic. So the anion-like growth is allowed, and you can grow a perfect vertical nanowire. What happens if we are inverting the polarity? Look, this is the nucleation seat. In this case, it's zinc telluride. Instead of terminating in tellurium, I reverse the polarity, and here, instead of growing vertically, we are allowing the growth in 3 different directions, but not vertically. So instead of a nanowire, we can grow this really nice tripod. Okay? So just changing the growth conditions, we can select the polarity of the initial seat, and then change the properties of the material. We can do it even more difficult by changing the growth conditions, and instead of growing vertical nanowires or tripods, we can do it very difficult and create this type of tripods. In this case, there are 2 types, and the thing is that we need something different. We cannot think about the normal octahedra, but if instead of the normal octahedra, we have this truncated octahedra in the 1-1-0 plane, or this other one in the 1-1-2 plane, what we have is one direction that is allowed for the growth, only one of them. We think about a second nucleation event here, creating a second octahedra, and then we will have 3 other possible anion-terminated surfaces for 3 other legs. So in this case, we end up with one tetrapod here with only one leg on top of the substrate, or with this other tetrapod with 2 different legs on top of the substrate. So just think about it. It's so easy. Just think about polarity. It's an easy rule, but you can understand all of these growth mechanisms. So just by dominating this, you can think which is the shape or which is the morphology that can be better in your applications. So I promised you to talk about 2D materials, and until now there was no 2D materials. So understanding what was going on before with polarity, it's easy now to understand how can we grow these nanobelts. So in the case of a nanobelt, it's just a kind of nanomembrane that it can have a, let's say, a controlled width. But in some other cases, we can create a kind of nanomembranes. And if you look at the atomic scale, what you can see here, this is a kind of gold catalyst in which the material can grow to this axial direction. In this case, when you analyze the direction, this is the 1-1-2 direction, not the 1-1-1 that I told you before. So this is a reason why this material can grow up as a nanowire, but at the same time, when you check at this flat surface here, you can see that this is perfectly flat. So there is no growth on this direction, but at the other side, there is some tapering. So this tapering is allowing the material to grow to the other direction. What is going on here? If you check the atomic scale, you will see that in this direction, you have 1-1-1 atomic planes. On this side, this surface here is terminated in the cation. So growth is not allowed to this direction. But on the other side, this 111 facet is terminated in the anion. So the growth will be allowed, and you can extend the growth. This is a kind of overgrowth during the growth itself, but you will be able to extend the growth to this direction, creating this type of 2D layer. So polarity is really helping here to grow these 2D materials. We can do it even more difficult. We can try to grow these really nice V-shaped nanomembranes, and in this case there is but another problem also related to polarity. The point is that we start by synthesizing this type of, let's say, pyramidal seed. This seed is terminated in two 111 facets, and of course terminated in this case in arsenic. This is indium arsenide. So as the arsenic is terminating these two facets, we will be allowed to grow in those directions. In this case, we are growing one wing of this V-shaped nanomembrane to this side and the other one to the other one. But if both of them are taking the anionic polarity, what is going on exactly in the middle? When both of the wings are merging exactly in the middle, what we have is that there is an inversion of polarity. And this is really damaging the electronic properties of our material, because if we want to use these V-shaped nanostructures in order to have a conduction from one side to the other, we could think about that. This is indium arsenide. It could be useful for that. But then, first of all, we need to simulate what is going on here. Imagine that there is no interface without a boundary. Imagine there is an interface without not a change of polarity. And imagine that we have, that is the case, that we have an inversion polarity boundary. In the case of an inversion polarity boundary, what we have, it's a perfect suppression of the conductance of our carriers. And this is why some potential barriers, electrostatic potential barriers, are created exactly at the position of these inversion domains. So if we want to have a ballistic regime of the conductance, here the different carriers will be scattered, here the electrons, here the holes, and then they will not trespass. So in this case, inversion domain just in the middle will destroy the electronic properties of this material. This is why it's important to understand what we have at the atomic scale and then understand what is going on here. So now I will show you another example on how we can change from the formation of one nanowire to the formation of this really nice nanomembrane only by creating one single defect at the beginning of the growth. So first of all, let me explain how we grow these really nice indium antimonide nanowires. Indium antimonide is a really interesting material because it has a low band gap, so it's good for these low energy or low power consumption electronics, but it's also really interesting because it has a really huge mobility. So the material is very interesting, but anytime that people has tried to grow indium antimonide on top of indium arsenide substrate, the problem is that there is a strong mismatch and a lot of misfit dislocations are created. These mismatch dislocations are propagating along the material and they destroy completely the mobility that it should have, or at least the mobility that it has been calculated in the bulk. So the idea was, instead of using thin films, let's grow a nanowire on top of another nanowire, and then we will get rid of these misfit dislocations because the mechanism of strain release in these nanowires is just perfect, as you will see now. So what we have is that both of the nanowires have this hexagonal cross-section. They are terminated in 110 planes, and under the growth conditions that we are using, the growth is not allowed along these 110 facets. So this is something that has to be kept in your mind. So what we see here is that the indium arsenide is crystallizing in this zigzag structure, so it's hexagonal, and the indium antimonide instead is cubic in the ABC stacking that I was showing you before. What we have here is the indium arsenide with the hexagonal structure, but just in the middle, when we switch from arsenic to antimonide, we have a kind of intermediate region where there is a strong compressing strain of 5.5%. After that, there is a formation of two single misfit dislocations, and after that, the material just grows perfectly without strain and relax. So if you have here, you have a perfect indium antimonide nanowire without a strain and perfectly useful for applications. So what we can see is that if we take into account this region here, we can compare the brightness of these dumbbells, and we can see that there is a replacement of the anion slowly. So the arsenic is slowly replaced by antimonium, and then what you have is that after this 5 nanometer region, the material is again pure with indium antimonide. So after that, you have these misfit dislocations just here, and after that, the material grows without any strain. And this is the simulation of the same thing here. So what's going on in the case of these nanomembranes? We have exactly the same mechanism at the beginning. There is a release of the strain, there is plastic and elastic deformation, but after that, the material just grows perfectly without any difference. But there is also this replacement of the, let's say, of the anions in this intermediate layer, but after that, it's all the same. So what is the main difference that makes this material to be created in 2D instead of 1D? If you check it in more detail, you will see that exactly at the interface between the indium arsenide and the indium antimonide, there is the formation of one single twin boundary, only one. And this twin boundary is doing the following. What you have here is that all your facets here were terminated in a 110 facet. In that case, the growth is not allowed. But when we are creating this single twin boundary, what we are doing is breaking the symmetry of the material and creating a new 111 layer. And you can tell me, how is terminated this 111 layer? So it's terminated in antimonium. So the anion is also focusing and letting the material, after breaking the symmetry, creating this 111 facet terminated in the anion phase, and then you can see how the material can grow again to that side. So because of that, we can create these perfect nanomembranes. And it's important to take into account also the catalyst seed. This is a catalyst seed after the growth. It's perfectly crystalline and epitaxial, but during the growth, this catalyst seed is liquid. So the problem is that in some of the structures, this liquid droplet will be the cause of the creation of this misfit dislocation, of this, twin boundary dislocation. And I will show you what. So this is the mechanism. I will try to illustrate with this map. We have the indium arsenide with a droplet. This is a gold indium droplet. But you can see here, these are the 6110 planes. And the good thing is that when you are introducing the antimonium inside the process, the droplet just grows a little bit more. In that process, 30% of the droplets cannot stand on top of the material, but just fall to one of the sides. And in that precise moment, they create the single twin boundary. And at that time, they break the symmetry of the material, they create this new 111 facet, and they allow the material to grow to this other direction. So you can tell me, is that interesting for the electronic applications and the quantum applications? Yes, it is. If you check, for example, the mobility of this material, you will see that maybe it's not as good as the bulk material, because it's 7 times lower than the bulk material, but I can tell you that it's 4 times bigger or higher than any other thin film with exactly the same thickness. So if you check the literature, this is 4 times higher, the mobility of this material, of any other thin film of 70 nanometers, like it is in this case. So you can also check the mutual path of the electrons, and you can see that it doesn't depend on temperature. So this can be that the dispersion or the scattering of these electrons is not due to the phonons. So in this case, we can have ballistic regime, and it can be explained that you can have this perfect, let's say, quantum confinement behavior of this material. So it's perfect to have this high mobility. You can create this transistor with high mobility right here. So let's talk a little bit more of this kind of 2D nanomembranes. And in this case, I will illustrate how we can analyze this type, in this case, gallium arsenide, aluminum gallium arsenide nanostructures. The idea here was to have this type of membranes with quantum wells created inside, on top of the membranes, you will see. So in order to analyze and get to this really nice image, you need to prepare the sample in the proper way. So I will show you how we did it. So this is the final shape I will show you. But, oops, sorry, there's a video in between. Hope it will work. Yes. So with this video, I will try to illustrate how it works, the sample preparation and all the analysis. So this is the shape of the nanomembrane, and inside you can see that the nanomembrane is composed of gallium arsenide in the middle, then aluminium gallium arsenide barriers, and then for the quantum confinement, and then in the middle again gallium arsenide. So this is the quantum well that is created in the middle. So this is the complete nanomembrane. This is the shape and all the atomic. I mean, this is a little bit squeezed. It's not as big as the real one. So it can be like 10 times smaller, but otherwise it's impossible. These are like 200,000 atoms. It's the most. I mean, it's the top that we can simulate. So this is exactly how it looks like, and then when you rotate at 19 degrees, you can see exactly this shape. So every single point here is an atomic column, and we are able then to understand and see how it's going on and what is the performance of this really quantum, let's say quantum nanomembrane. So the process here is quite similar to the one of the nanowires that we were analyzing in 2013. So what we have is that exactly in the middle, we have pure gallium arsenide. It's the same that we have here in the nanomembrane. This is a nanomembrane. You can continue like this, and you could see the whole nanomembrane. So we were growing like aluminium, gallium arsenic on top. But due to the different diffusion of aluminium and gallium, what we get is that the aluminum is mainly incorporated on the edges of these, let's say, hexagons. It's exactly the same that is going on here. So what we have is a kind of confinement, like here, that it has a kind of quantum dot confinement. So what you can see here is that from time to time, this, let's say, accumulation of aluminum, due to some defects, for example, this H is a 112H that has been created, you see that there is a bifurcation. It's kind of fork shape that is dividing the aluminum, but is living just inside a rich region with gallium arsenide. So this is in fact a kind of gallium arsenide quantum dot, perfectly confined, but this aluminum-rich gallium arsenide shell around. You can see it here in more detail. Let's see. Yes. So this is the bifurcation of the aluminum-rich layer. This is how it divides. This is the edge terminated in 112, and this is a kind of, it's not a pyramid, but it's kind of pyramid. It has this shape. It's a little bit more complicated. Just inside, you have a quantum dot that is gallium-rich. Okay? So if you take into account this material, you can see, you can do photoluminescence, you can work in cathodoluminescence as well, and you can see the single photon emission that is produced by these quantum dots. So you cannot control exactly where these quantum dots are formed, because these are kind of defects, but you can assure that in every nanowire or in every nanomembrane, you can find at least several of these quantum dots. You can see that there is a blue shift that is normal because there is a quantum confinement, and the line width are below this 100 millielectron volts. So it's quite really good, and you have the behavior is kind of a single photon emission. So you can use this type of structures for future quantum computing, for example. So let me talk also about some other nanoflakes and nanomaterials. I told you that I will talk also about these really thin layers or monatomic layers. In this case, what we did is creating these honeycomb-like hematite nanoflakes. And what you say is that by electrodeposition, you create these manganese oxide nanoflakes. By this hydrothermal method, you introduce the iron, and you get these iron nanoflakes. And then with polypyrrole, by electropolymerization, you create nanowires on top that are mostly formed by this polypyrrole material. Also, it has a little bit of iron, and this will reinforce the properties of this material. So in this case, when you check it in the microscope, you see the perfect composition. So this is the initial iron-like, let's say, honeycomb-like nanoflake, and then you see that the iron is also introduced inside the polypyrrole. We cannot detect directly the polypyrrole, but we can detect the nitrogen, which the polypyrrole is rich in nitrogen. You can see these kind of wires that are flowing from the initial nanoflake, and you can see that the iron is also right there. Similarly with these other shapes. So what we were using this is for supercuts, and we could see that the specific capacitance, it was kept up to 97% after 3,000 cycles, so it's a really good material, and compared with some others in literature, it was not so bad. So that was a good application in order to use this, let's say, 2D materials. So another thing that we were doing is analyzing, for example, the mechanisms or the processes in order to get this type of 2D nanostructures. These are nanoflakes, and initially we were starting with a molybdenum oxide, and we wanted to create a sulfurization process, and we wanted really to analyze how the process was going on and what was occurring inside the material. So it was important to determine where the sulfur was situated and what was the difference between the oxygen and the sulfur and how the sulfur was incorporated inside the material. So when you go to the atomic scale point of view, you see that the sulfurization is perfect. You have several monolayers here around, and you can see that it's full of misfit dislocations as well. And it's important to know that in this kind of materials, whenever you have defects, there is an improvement or an increase of the active sites for the catalytic processes. So as far as you have many more of these defects, you are increasing the active sites for the material. So this is also important in the case of molybdenum sulfide nanoflakes. It's important to see exactly if this is a monolayer or not. It's good to identify the sulfur sites and the molybdenum sites, but the most important part is not just on top of the flake, but it's in the grain boundaries and also at the edges of the material, because those are the parts that are more active for the photocatalysis, for example. You can use it for water splitting, for hydrogen evolution reaction, for oxygen evolution reaction. But it's important really to understand which are the defects that you have in order to simulate them and understand all the physical and chemical processes that are occurring there. So these are just fresh images obtained at SuperSTEM with Quentin Ramas. And you can see here how, okay, what we wanted to know is this is a grain boundary, and we wanted to know exactly what was the atomic distribution at the grain boundary, because then by DFT, I will not show it here because it's not published, but by DFT, you can calculate the efficiency of these grain boundaries and these defects towards the evolution reaction of hydrogen or oxygen. You can see here, this is a grain boundary, and you can see the movement of all the atoms. Even here you have a single atom of gold that is moving around. You can see how it's displacing from one side to the other. So it's important, not only the grain boundaries, but also the edges, and you can compare and understand how they are evolving and how they are behaving inside the material. So I hope, I think it's time to finish. So I hope that was I could explain you how important it is to know at the atomic scale how to understand your materials, because this can explain not only the growth mechanisms of these materials, but also the properties that they have from an electronic point of view, photonic, but also for chemical applications. So the next and future generation of microscopes for sure will include in situ applications in order to have the reactions exactly inside the microscope and see all these processes but in working conditions. And that is the amazing future of microscopy. So just let me thank all the collaborators. You will see that Arbiol. These are people that were growing most of the materials shown here. Also some other growers and collaborators, and mostly a lot of different places where we also collaborate for microscopy experiments. So just let me thank my group. Pongi was working in this type of nanoflakes, the last part of the work, and the first parts of the work were done by Maria, Reza, and Aziz, which were former PhD students. So thank you very much for your attention.
Thank you for this fantastic talk, all these nice images, of course, also animation. So I understood that if we invite you in the conference in next year, you will show us instead of video for growth of a model, it will be the real nanostructure growth.
We are working on that right now.
Okay. So the talk is open for questions. Who wants to start?
I was too fast.
You said the difference between the two structures is just polarized direction.
Yes.
Oh, if I want to know which structure is minimized energy, how can I measure or how can I understand?
It depends a lot on the growth conditions. It depends if you are using a catalyst or not for the growth. It depends on the substrate. It depends in many, many things. So every different material, every different type of growth, you have to simulate separately. So for the typical growth conditions that people were using in the last, let's say, 10 years, they were growing with this anion-like polarity because it was the one that was giving the people a fastest rate of growth and a better yield. So they just chose that conditions because it was good. But those conditions were at the same time introducing a lot of defects in the nanowires and the nanomembranes. Nowadays, people is trying to grow on the other side with the other polarity because although the growth is slower, the quality of the nanostructures is much better. So we are also working on this right now.
Direction, polarization, the conductivity is the same or not? Because maybe some direction is a semiconductor or some direction is semi-metal. How we can understand the conductivity of these two?
The conductivity with the polarity is not changing as soon as you don't contact with another material with reverse polarity. I didn't show it today, but we had an example. I told you that all those materials were growing with the anion polarity, but there was one exception, that was zinc oxide. So in one experiment, in one paper that we had, we were creating a PN junction with gallium nitride and on top zinc oxide. Gallium nitride was growing with the anion polarity, and the zinc oxide, we tested, and it was growing with the cation polarity. And then what you had just in the middle was an heterojunction with an immersion of polarity. And that was creating, when you were calculating, because we had DFT calculations on what was going on, you have a different band alignment depending on the polarity of both systems. So we were simulating all the different possibilities with A polarity with B, with A with A, B with B, and B with A. And we had different types of band alignment with completely different properties. In our case, it was one of the options, anion with anion in the gallium nitride and cation in the zinc oxide. And what we got is that exactly at the interface, we had a two-dimensional electron gas that was accumulated there, and it was giving, thanks to that, we could explain the optical properties that we could see. But it's changing in
the molybdenum of dioxide does not exist. Molybdenum trioxide. You said molybdenum dioxide and molybdenum T-sulfide.
In that case,
dioxide is not exist.
We checked it.
Trioxide because when you do T-sulfide, it exists. It's layered, but molybdenum dioxide not.
It's not in a 2D layer. No, but it's not a 2D layer. No, it's a nanomembrane. It's dioxide, but it's a nanomembrane, so it has a thickness. It's not a single layer.
Okay, I would maybe, we can discuss later. I would wanted to give possibility to other people also to ask.
Professor Arbiol, I have a question about this movie about the droplet, liquid droplet on the top of the cube. You thought that droplet is falling down. And what is the driving force? Even gravity or adhesion?
So when you are at the nanoscale, gravity plays a role, but I don't know if it is the most important force. But at the same time, you need to think that the size of the diameter of the nanowire is quite small, but the particle on top is really too big. So it's not that it falls, but it's wetting one of the sides. So at the end, there is no more space. It's trying to be kept on top, but at the end, it has to wet one of the sides. So this is only occurring in 30% of our cases. In the other ones, we just get nanowires. when we select the best conditions we could get, it's only happening for 30% of that.
So next
In
year
that
we want
case-
to see it in situ.
In
right?
situ.
Well,
Well,
not
then
drop, but
go to look. They have a really nice microscope for in situ growth of nanowires.
okay, one last question.
In water splitting device, you have used the electrode using MOH to MOO2.
Yes.
Okay. And I want to know which part, which material, MOH2 or MOH2, which plays the important role here to enhance the catalytic sites.
In that case, we were more interested in MOS2.
MOH2.
Yeah,
Different morphology.
Yeah, the oxide was only used as a pattern in that case.
Okay.
So what we were interested is, I mean, we didn't produce the material. It was produced with Anna von Kuberta. In this case, it was Esther that now she's in Amsterdam. So she's the one that was producing, but the interesting thing was not the molybdenum oxide, but the molybdenum oxide was just a template. And after that, we were trying to sulfurize that in order to get the molybdenum sulfide.
Okay, thank you.
So one last question.
So when you proposed those growth mechanism, did you propose based on the pictures you see first, or did you just propose that based on the simulation you did?
Good question. Sometimes it's both. So you see the properties of the material at the same time you are analyzing at the atomic scale, and you need to mix everything to match somehow in order to understand. So sometimes it comes more from the properties, sometimes it comes more from the atomic scale. But you always discover new things, and you can propose new changes in the growth mechanism to the growers, and that it's just a really, let's say, really matching collaboration. It really helps.
In 1 year in situ.
Yes.
Okay, good. I will close this session now, and we meet after lunch.